All right, in section 3, we're going to try to prove trig identity is true. So very similar to what we had before, where we were trying to manipulate an expression and get it to equal something new. In this case, we actually know what we're trying to manipulate it to, and we're just trying to prove that this statement is true. So there is not a lot of new things I can tell you about this. It's very similar to what we did before. The only difference is we know what we're trying to go. So for example, if you look at this one, I am telling you that sine times secant equals tangent. I want you to prove to me that it is true. Now the way we usually do this is we are going to basically start on one side, doesn't matter which side, and I'm going to prove that it equals the other side. So generally speaking, we like to start on the side that has more things that I can change using my fundamental identities. But honestly, it does not matter. You could do it either way. So in this first proof, where I'm trying to do sine and secant equals tangent, I would obviously start on the left because there seems to be more to change there. And so I'm going to ignore the right side, and I'm going to try to change the left side into the right side. Now, the one big rule I can tell you, in general, if you turn everything to sine and cosine, generally things work out a little better. And we can do that because we have a relationship for every trig function to turn it into sine and cosine. Cosecant and secant are reciprocals. And cotangent and tangent, remember, are quotient identities. Cosine theta over sine theta and sine theta over cosine theta. So we can turn anything into sine and cosine. The only other thing that we might encounter is if we see things with squares, sine squared, cosine squared, cosecant squared, then those are probably ones we will use with our Pythagorean identities. So let's go ahead and take a look at sine secant equals tangent. This one's a pretty straightforward one. If I turn everything to sine and cosine, well, sine doesn't change, it's sine. And secant is 1 over cosine. Now remember, when you multiply fractions, you can consider this sine over 1 or just sine. We multiply straight across. So this will give us sine x over cosine x. Well, we know sine x over cosine x is tangent x, which is exactly what I'm trying to prove. So as long as you turn one side into the other side, that is considered our trigonometric proof that we have proved this identity to be true. So let's look at another one. This next one's very similar, a pretty straightforward one. Cosecant we know is 1 over sine of x. And tangent is sine over cosine. Now, very similar to when we simplify expressions, when we have things on top and bottom, we can cancel them out as long as it's multiplied. So we end up with 1 over cosine x. And up above, we know 1 over cosine is secant, and that is what we're trying to prove that this equals. So it's almost easier because you know what you're trying to get to, you know what your final answer is going to be, instead of just trying to manipulate it randomly and get some values. Let's look at this one. This one's a little trickier. So if I was going to try to simplify this one, first thing I would look at and think of, okay, what side am I going to start on? There's no real good way, but if I had to guess, I would say let's go ahead and start on the left. Mainly because I see an expression in front of a binomial expression, so that generally means distribute. So I get sine theta cotangent theta plus sine theta tan theta. Now somehow I'm claiming that this is going to simplify to simply secant theta. Let's see if it does. So first I would turn cotangent into cosine over sine. And then I would turn tangent into sine over cosine. Now if I look on the left side, this cancels out. So what I'm left with is, see what we have. We have cosine theta Nothing cancels out on the right side, but I notice I have two sines on top, so I'm going to make this sine squared over cosine theta. Now we're kind of stuck here. This is a very, very typical kind of problem. When you're adding things, remember, when you're adding things that are fractions, we need to find common denominators. So that's what I will do in this case. This has a denominator of cosine, the other one has no denominator. So I'm going to multiply top and bottom by cosine theta, which I'm allowed to do. Now the benefit of this is, do you notice that you get cosine squared plus sine squared all over cosine theta. So cosine squared plus sine squared just from the numerators, and then cosine because it's our common denominator. But sine squared plus cosine squared is one of our Pythagorean identities. It is our primary Pythagorean identity. Cosine squared plus sine squared is just 1. So I can replace cosine squared plus sine squared with 1. Which leaves me with simply 1 over cosine, which is secant, which is what I'm trying to prove this to be. So this brings up one of the most typical problems in proving identities when you're adding fractions together. Anytime you have fractions, anytime you see things that are added together, more than likely you are going to have to use common denominators. So this is kind of a common denominator problem. We'll have a couple other different types of problems that we'll reference here in this section. So here is another one. This is a very famous one where we have cosecant squared y, cosine squared y equals cosecant squared minus 1. Now there's not a real clear way to start this one. Honestly, I'm not sure either side is really easier. Generally speaking, if I don't see one that's clear, I always go with things that are multiplied versus added or subtracted. So since the left is added or subtracted, I would probably start there. So I see squares, so what I would probably do is start with one of my Pythagorean identities. So I have a couple I can choose from. I have this one for cosecant, which is cosecant squared equals 1 plus cotangent squared. We also know that cosine squared is 1 minus sine squared. That is our rewrite of our Pythagorean identity. So I'm going to probably try to use one of these two. Quite honestly, it doesn't really matter which one you do. Generally, I would probably try to use the cosine before I use the sine, so maybe I'll try that one. So I'll go ahead and try to use this one. So I'll replace the cosine squared with 1 minus sine squared. Maybe we'll do it both ways just to show you it works both ways. So let's say I do this. So I have cosine squared replaced with 1 minus sine squared. So then I'll distribute. So I'll get cosecant squared y minus cosecant squared y times sine squared y. Now, this is good. I want cosecant. That's good. I want cosecant squared minus 1. So I don't really want to change that. But if you look at the left or the right one, I know cosecant is 1 minus sine squared y times sine squared y, which will cancel, and I end up with cosecant squared y minus 1, which is what I wanted, So there are definitely different ways to go. I think this is probably the easiest one to use, but again, there are lots of ways to do these proofs. So I will warn you, sometimes you go down paths on these and they will not go very well. Do not be afraid to go back and start again. So maybe if you started this one, maybe if you start with this one, just looking at that, that's going to be a nightmare if you go down that path. So maybe go and try something else. That might be to your benefit. All right, let's look at this last one. This is what we refer to as a conjugate problem. Also a pretty famous problem in trigonometry. Because a conjugate problem, you'll notice you have two of the same things on both sides that are conjugates. Conjugate meaning one is plus and one is minus of the same two terms. So when you have something like this, it honestly doesn't matter which side you start with. But the way we generally will work this is we will multiply both sides by the conjugate. Or not both sides, pardon me, the top and bottom by the conjugate. So I will multiply the top by 1 plus cosine beta and the bottom by 1 plus cosine beta. Now the benefit to this is now I have my 1 plus cosine beta on the bottom, which I want to end up with on the bottom. Because remember, I'm trying to turn the left into the right. Or vice versa, you could do the right into the left. It really is about the same proof. So down here on the bottom, I'm not going to distribute it in. I certainly could distribute the sign in, but I don't want to because remember, I want a 1 plus cosine beta in my answer. Now for the numerator, we have these two binomial expressions. I am going to FOIL. So 1 times 1 is 1. 1 times cosine beta is positive cosine beta. Minus cosine beta for the inner, and then minus cosine squared beta. So anytime you have two binomials, you'll just FOIL. So what we'll end up with, these will cancel. So on the top, we'll get 1 minus cosine squared beta over sine beta times 1 plus cosine beta. Now, if you remember, one of our rewritten Pythagorean identities is 1 minus cosine squared beta equals sine squared beta. So I can now replace the top with sine squared beta over sine beta 1 plus cosine beta. Now, we're almost there because notice I have two signs on the top, one on the bottom, so I can cross one out. So I end up with sine beta over 1 plus cosine beta. And that is our proof. That is what I'm trying to make it equal, so that's what it's going to be. All right. So there's just a couple introductory proofs. We'll obviously do more in class. We'll do more practice as we go through this section. If you do have questions, obviously, please do let me know where you get stuck.